All right, everyone. Welcome to our last class of, I guess, learning. We're going to talk about the definite integral today. And then on Thursday, we'll have our final. It'll be over the whole class period if you need that much time. I have not made the final, but I can tell you it'll be, it'll have the same or fewer problems than the review does. And then you can also use one reference sheet for the test. So you just need to make that, and you will submit that with your work. All right, so that sheet that you make, you're going to have to turn it in with your work. But get that prepared before class, and just make sure that it does not have any worked out problems. Okay, that's the big thing. All right, no worked out problems.
Is that a just an index card, like the measurement item? That is that what that is?
8.5 by 11 standard sheet of paper.
Oh, okay, gotcha.
Yep.
You say steps and procedures. Do you mean we could like write down a list of like to find or critical numbers, take derivative then, or something like that along those lines? But we just can't have actual problems on there.
That's right.
Okay.
Yep. Inflection points are where you have a change in concavity, right? Things like that.
Okay.
So whatever you think might help you. Okay.
And is that both sides or just one side?
Both sides.
Both sides.
You can handwrite it. You can print it, copy, I don't care how you do it.
And there won't be any related rates on this, will there? You said, right?
I thought there was related rates on the review, one of the reviews, no?
Yeah, the
You
one you
said
sent with the
32.
solutions.
Okay. I mean, that's fine. I was just waiting to know.
Yeah. There could be. I think when you were tested over it, I gave you a couple of problems to choose from. I think on the final, it'll just be one problem, and it'll probably be on the easier end of the spectrum, just to make sure that you can demonstrate you know how to do
Sounds good.
it. Okay. So we ready for today? Any questions on substitution? Any of the homework problems or anything that you want me to cover on that?
I'm okay. The substitution, once you see the pattern, you start to really notice it, and it kind of starts to fall into place, at least for me.
You'll see it again in Cal 2 if you're taking Cal 2. Oh yeah, and I did send out an email. I hope I sent it to the right class, that they're upping my face-to-face class by 3 seats. So if anyone is interested in that 9 a.m. Monday, Wednesday class in the fall, I'm not sure when those seats are going to open up. So I don't know. I guess I could check real quick to see if they're open or not. Let me see. Oh, yay, I have 17 in there now. So let me see. Oh, you know what? I can't open that page. Let's do this. Yeah, they haven't done it yet. So I gave them they asked me if it was okay. I said it was fine yesterday, so we'll see. Okay, are you ready? Definite integrals. So what we've learned so far is that if we have this notation, that this means that we are going to find this thing, capital F of X plus C, and that this will represent the general antiderivative of this function F of X. And the dx, remember, was something that helped us keep track of our variable, but it became very important. The dx became very important when we were doing substitution, because we would use that to do our substitution and get everything switched over to a different variable. So what I'd like to do now is introduce you. Oh, this is called the indefinite integral. I already told you this a while back. But the word indefinite, the way I think about it is like When you're sure of something, you definitely know something, right? Then that would be definite. Indefinite would be you don't quite know something. And that's what this plus c is. It's like we know the antiderivative, but we have this plus c, which is a family of functions, right? So we narrow it down to a family. We now talk about something called the definite integral, which is going to have a completely different meaning. The answer is going to have a completely different meaning to us. But I have to give you like the motivation behind it. All right, so here's the actual idea. Okay, so this is not a chapter in the book. So I've just made up my own notes on this. This is called Riemann's sums, and Riemann is a mathematician, okay, who kind of was one of the pioneers of using this method. So let's get into the idea. Forget Riemann for right now. All right. Our motivation for all of this is what's called the area problem. All right. So what is the formula for the area of a circle? Right. We all know the formula for the area of a circle, right? The area of a circle is pi r squared. Pi is this really weird number, right? But this will give you the area of a circle. If you know the radius, you've got the area. So the question is, where did that come from, right? Where did that formula actually come from? Because everyone knows it, but no one knows where it came from. So if we didn't know the formula, okay, if we didn't know it, how could we estimate the area of a circle? So let's say I get like a string with a pencil, and I hold the center of the string down. I draw a circle, with the string and the pencil. I draw this really, accurate, precise circle. How could I then estimate the area of it? Well, one thing we could do, okay, is let me draw my circle here. So let's say we had this circle here, all right, and I wanted to estimate the area. And I know the radius, okay? So I know the radius, r, check, I have it, okay? But if I wanted to estimate it, what I could do is I could draw maybe a square. So imagine that I have a ruler, okay? A ruler, and maybe I should take one step back. Think of historically human beings, okay? As we were trying to advance, right? We started counting, and then eventually we had property, right? People started to say, this is mine, that's yours, stay off my property, right? Like, don't go across this line. We all know that properties are not always straight, right? The property lines are not always straight. Sometimes you have a river, and you've got this person here that has some property here, and then their neighbor has some property there, and another person has property here. So these property lines are not always straight. So if we wanted to know the area of this, well, that's hard because this is curved, right? So how do we find the area of shapes that have curves to them? Well, the most basic shape is a circle, right? So if we can start with that, maybe we can find a way to figure this out. So for thousands of years, human beings were trying to figure out a way to find the area of a circle. And they said, okay, well, we can find the area of squares and rectangles, right? If I have a rectangle, length and width, the area is length times width. And that, we were happy with that for a long time. I mean, we were just like, yeah, we can do that all day long, if it's a rectangle or a square. Even a triangle, we were okay, right? Because area is half base times height. But it was these weird shapes. So if I'm trying to estimate this area, okay, if I'm trying to estimate this, then what I could do is draw a square, and I could find the area of that square, right? So I'm going to shade it because that means I know the area of that. So whatever that is, I write it down. And then I could come in and draw another rectangle, maybe right here, and I could find the area of that. And then maybe another rectangle right here and find the area of that. And another one over here, find the area of that. Maybe down here, right? So if I add up all these rectangles areas, I would have an estimate, right? It would be estimate. It wouldn't be a very good estimate, but I could do smaller rectangles, right? I could start filling in all these little gaps with smaller little rectangles. And sit there and measure and write things down and measure and write things down. And I could just draw as many rectangles as I possibly could, but no matter how many I draw, I'm always going to have little gaps, right? I'm going to have these little curved gaps somewhere in here. And that's going to be the error that I would have, right? This is the error. All of those added up. So imagine we have all these rectangles, right? All of these rectangles we've put together and we've added them up. Would you agree with this? The area of those rectangles that I drew is going to be smaller than the area, the true area of the circle, right? Because I have all these little gaps I didn't get accounted for. So we could do that, right? Okay, well, what if we take that same circle and this time, instead of drawing a square inside of it in a bunch of rectangles, what if I draw a square around it like this? I could find the area of that, right? And then I could draw smaller little squares and rectangles in here and start subtracting those areas from the big square, right? So I have the area of the big square, and then I start subtracting all the little smaller rectangle areas that I find on the inside. Now, when I do that, I'm still going to have little gaps, little errors here, right? That I didn't account for. So it's not going to be perfect, but it'll be an estimate. Now, would you agree with this? The area of these rectangles would be bigger than the true area. Do you see that? Because you take the big squares too much, you start taking away these smaller pieces, that would be too much, right? So what we could do is we could say, all right, if we do the first method, we get some area. I'm going to call this rectangles A, okay, for doing it this way. I'm going to call this rectangles B for doing it this way. If we do this, then what we're going to have is the true area is stuck between two numbers. It's stuck between the rectangle B method, which is this method. It's smaller than that, but it's bigger than the other method where we did rectangles on the inside. That makes sense? So what we've done is we've said, okay, give me a circle. I'm going to draw these rectangles, and I can tell you that the true area is between these two numbers. And the better I get at drawing rectangles and the more rectangles I draw, the more narrow that window becomes. Do you all understand that?
Yeah, so then just basically the area of rectangle A and the area of rectangle B, does that become our values for the integral of what it's going to where, you know, so.
Well, we're
I'm
not
trying to say
talking
that, but-
integrals yet. We're not talking integrals at all yet. I'll get to that.
I was
Yeah.
just looking ahead, but okay.
Yeah, I'll get to that. This is just more of an idea. The idea is that by doing these two things, I can squeeze the true number between two numbers. And the more I'm willing to draw, the more rectangles I'm willing to draw, the more narrow this window becomes. And the more accurate my estimate becomes. Understand? But this can be tedious, right? Can you imagine someone sitting there with a ruler, like drawing little rectangles and trying to find areas? Can you imagine doing that without calculators or computers or anything else? Well, this method actually has a name. Okay, you'll get a kick out of the name. It's called the method of exhaustion. Okay, because you basically are going to exhaust yourself doing it. All right, you're doing all these rectangles in there, and the more you do, the more accurate you get. The Chinese did this to a precision that is just remarkable. And they were actually able to get it so good that they were able to determine that the area of a circle was approximately 22/7 r squared. Not pi r squared, but 22/7 r squared. And if you do 22 divided by 7 on your calculator, this is approximately
Hello?
3.1428.
Yes,
Hey, this is Cindy over at Dixon
Five.
Automotive.
Yep.
Hey, they got the transmission flush and everything done.
This is what they came up with, all right? Where pi is actually, pi is approximately 3.14285. Oh, wait, sorry, oops, that's not right. I was like, wait a minute, I'm writing the same number down. Pi times 1.0. So yeah, 3.1415927. So the Chinese were able, with this method of exhaustion, were able to get it close enough that they got the 3 here, they got the 1, they got the 4, and they were off. So they got it to the nearest hundredth. It's different than pi in the thousandth position, but that's not bad for just rulers and pieces of paper, right, to get it that precise. But the idea, though, is what's important here. And you would never want to do this, right? Like you would never in your life want to sit here and actually do this by hand. It would be a tremendous challenge. Okay, so with that in mind, what if we wanted to find the area below a curve? Okay, so imagine that we have some curve, some function, and we want to maybe start here at some point A, go to some point B, and we're interested in the area below the curve, right? And also we know the function, f of x is given, all right? So if we know what this function is, and we want to start somewhere and end somewhere, and we want to find this area, okay? So we're interested in that area. The question is, how can we approach it, right? How can we approach this? So one approach, and this is what Riemann came up with, is that you could take rectangles. And so what you do is you pick some arbitrary point. Okay, so we're going to go from 1 to 5 in this example. And we're looking at the function. Right now we're looking at x squared. So this is the function f of x equals x squared. So what he said is, let me do a couple fewer points right there. So what Riemann is saying here is what we can do to estimate the area is we can cut this interval into 4 equal sections, right? So the distance between here and here is 1, the distance between here and here is 1, distance between here and here is 1, distance between here and here is 1. And he says, all right, we'll go to the end point of the first little interval here, to the right endpoint 2, plug 2 into the function and see what you get out. So what would happen if I plug 2 into this function? I would get 4, wouldn't I? Right?
Yep.
So we know that this rectangle right here is 4 units tall. And how wide is it? Even though it doesn't look like it. How wide is this?
2.
We go from 1 to 2,
Oh.
right? So this distance should just be 1, right? So do we know the area of that rectangle? 4 times 1 is 4, right? Then we do the same thing for the next rectangle. So this time go to 3, plug that into the function. 3 squared is 9. So we know that this rectangle is 9 units high. And how wide is it? 1, right? So what's the area of this rectangle? 9 times 1, 9, right? And then you just keep on doing that. This one would be what? How tall is this one?
15.
You're plugging in 4, right? So 4 squared is 16
Yes,
times the
16.
width, so 16. And what's the area of this one?
25.
25. You plug in 5 times 1, you get 25. So the estimated area is all of these rectangles added up. So 25 plus 16 plus 9 plus 4. If you add that up, you get 54. Now, the true area, I have the calculator doing it, I mean, the computer doing it for me, is 41.3. We're off by quite a bit, aren't we? I mean, we have overestimated the area. And the reason we've overestimated it, or why we're getting this answer, is because of all this stuff here. All this gray part up here, all that, we actually didn't want, right? We actually didn't want that. That goes past the curve. But it's an estimate, right? It's an estimate. So how would you get a better estimate? Using the same method, how could you get a better estimate?
Use more rectangles.
Do more rectangles. Because look, I'm going to kind of highlight the part that was bad here. This part's bad, this part's bad, this part's bad, this part's bad, okay? So now I'm going to do more rectangles. You ready? So watch what happens if I do some more. Do you see that? Let's see if I can erase this. Do you see that the error that we used to have, right? The error that we used to have here has now been reduced. Now our error is actually just this piece, that piece, that piece, that piece, that piece. Understand that the error got smaller here. And you can tell from the calculation that we got closer to 41, right? We're now at 44. And in this particular case, doing it this way, let me do here, 20 rectangles. So now I'm doing 20 rectangles instead of 4. So how could I get even better?
40 rectangles?
40 rectangles, right? And what would be better than 40?
80.
Let me do 40. Here's 40. So look at 4.1 is the 4.133 is the true area. 4.254 is what my estimated area is. But again, pay attention to the error, to the amount of error we have, right? Fewer rectangles, lots of error. More rectangles, less error. And if I could go out to, let me see, I have my computer stopping at 70 rectangles, and we're still off quite a bit, aren't we? The more rectangles, the closer we get to the true answer, right? So maybe the true answer is what we get if we let the number of rectangles go to
Infinity?
infinity, right?
Yeah.
What if the number of rectangles go to infinity? Then this should approach the true area, right? This calculation should approach the true area. So how do we let something go to infinity? Well, we take a limit, right? That's what limits are all about. So this is the idea, right? The idea is start out with the basic idea of just a few rectangles. We could do that by hand, right? We just did this by hand. Those 4 rectangles, right? We did them by hand. We figured out how wide is each one. And then to figure out the height, right? I'm going to draw it again. We knew that each one of these was 1. And the height, what we did was we picked this point, we plugged it in, we got that height. We picked this point, we plugged it in, we got that height. We picked this point, plugged in, and got that height. Picked this point, plugged in, and got that height. So we had to plug in 4 points, didn't we? Into the function x squared. So if I do 40 rectangles, I'm gonna have to plug in 40 points, right? If I do 100 rectangles, I'm gonna have to plug in 100 points. And if I do an infinite number of rectangles, I'm gonna have to plug in an infinite number of points. That's weird. That's weird. Also, think about this. Think about area. If I let the number of rectangles get bigger, tell me about how wide these rectangles are. What's happening to the widths of the rectangles?
They're getting progressively narrower.
Narrower. They're approaching what?
0.
0.
They won't get to it. But
The
they'll
width of
close.
each rectangle is approaching 0. And if it is 0, you should have no area, right? If I tell you a rectangle has 0 width, it has no area. So what we're going to want to do is let the width of the rectangle approach 0 without actually ever getting there. Again, that's what the limit's here for, right? The limit will allow us to do that. Okay, you ready? We're gonna try and take all these ideas and I'm gonna see if we can't come up with what Riemann came up with, all right? You ready? I don't think that this is one of those things that you need to like absolutely know and understand this. So I think it's more important for you to try and just pay attention to what I'm doing and ask questions as opposed to writing this all down and copying it. You can always go back and look at this, okay? All right, so let's see. In my history of teaching this, this is hit or miss with people, all right? Some people get it, some people don't, all right? But it's not one of those things that you have to absolutely know. Okay, here we go. So what I'm gonna do is I'm gonna try and come up with a general formula to be able to add up the area of rectangles. So I'm gonna start with a first starting point A and an ending point B. And then I'm going to have some function here doing something. And it doesn't matter what that function is, but that function will be f of x. And let's, again, assume that that's given to us, but we don't know what it is, okay? We don't know exactly what it is, but if someone gives it to us, we'll be in business, okay? In the previous example, it was x squared. Here, it's just some function. All right, I'm gonna start cutting rectangles. Ready? My first rectangle is going to go, I'm gonna go to the, let me do a different color. My first rectangle, I'm gonna go to the right to a point here. I'm gonna call this x1. I'm gonna go up to the function right there, and I'm gonna figure out how high it is, and I'm gonna draw a rectangle and come over and down. I'm gonna call that R1. So I'm taking x1, I'm plugging it into the function, figuring out how tall that is, and then making a rectangle out of this, and that's R1. Now I'm gonna do it again. I'm gonna move over by the same amount to another point, x2. I'm gonna go up to the function and then go over and down, and that'll be rectangle 2. Let's do it again. I'm gonna go over to x3. I'm gonna go up to the function, wherever the function is. I'm gonna go over, cross, and down. That'll be rectangle 3. All right? I'm gonna keep doing this, all right? And I'm not gonna put 10 rectangles. I'm not gonna put 20 rectangles. I'm not gonna put 100 rectangles. I'm going to put n rectangles, n. And I'm not gonna tell you what n is. I'm just gonna say n, all right? So when I get to my last point, right? My last point right over here, this will be B, right? B is actually the nth point, right? So rectangle 1, x1 was the right corner of R1. x2 is the right corner of R3. x3 is the right corner of R3. So this last point, x sub n, should be the right bottom corner of the nth rectangle we have in here. This is R sub n. Also, I'll point this out, even though we don't necessarily need this. Our first point, A, I'm going to call that x sub 0. Okay. Any questions on the drawing? Okay, now what I want to do is I want to talk about what is the area of rectangle 1. Okay, so what I mean by this is what is the area of rectangle 1? Okay, the area is going to be the height of it, right? What's the height of this rectangle? How tall is this rectangle?
Would be f of x1.
Good, it's f of x1. Everyone understand that? It's whatever you get when you plug x1 into the function. I don't know what the function is, but it's f of x1, whatever that is, okay? Now, how wide is it? This is the tricky part. How wide is that rectangle?
Would it be x to the 1 minus a
X to the 1 minus a.
for that
What do
rectangle?
y'all think? What do y'all think? X to the 1 minus a. So let's say that this was 4, and let's say that this was 3. Let's just say, right? This is 4 and this is 3. Then 4 minus 3 would be 1, wouldn't it?
Mhm.
Okay, I agree with that. I agree with that. And then the same thing for rectangle 2, you could say x sub 2 minus x sub 1, couldn't you?
Mm-hmm.
And for x sub 3, you could say, sorry, for the width of rectangle 3, you say x sub 3 minus x sub 2. I agree, that's not incorrect at all. But I want us to look at it from a slightly different perspective.
Gotta try a different
Javier?
method.
Um,
Okay, let's try it.
Would you find like the distance between those 2 points, A and x1, or no? Like on that.
Well, that's what we're trying to figure out is what is this distance, right? And Cody said, just take that number and subtract that number. And so I'm gonna write it down, but don't write this down. This would be correct.
Could
Okay?
I give you a
That is
general formula?
correct. Pardon me?
I said, could I give you like my idea of what the general formula would be? Would it be like x to the n minus 1 or something like that?
Okay, yeah, I understand what and I know where you're going with that, but I want us to take a step back even from that, okay?
Okay, sorry.
No, don't apologize, okay? All of these rectangles have the same width, don't they? Because I told you I'm gonna move across by the same amount each time. They all have the same width, right? So if they all have the same width, how wide are they? And I'm gonna help you by drawing another picture below this to help guide you. Let's say that this was 1, and let's say this was 5, right? And let's say I cut this into 4 rectangles. Oh, that's terrible. Let's say I cut that into 4 rectangles, whatever they are. If I cut those into 4 rectangles, how wide are each one of these?
1.
1. Okay. Right? Do y'all understand what I'm saying? If I do this into 4 equal ones, this is 1, this has got to be 1, this has got to be 1, this has got to be 1. Yes? You can get that by thinking about it this way. Take this endpoint, 5, subtract from it this endpoint, 1, and divide by the number of rectangles we have. How many rectangles do we have?
4.
We have 4, right? And if you do that, you get 4 over 4, and that's 1. That's how wide each rectangle has to be. So what you're really doing is this. You're saying, hey, what's the distance between 5 and 1, right? What's the distance between those two? So that's like what Cody was saying. Take 5, subtract 1. That would be the distance between them, right? 4. And then we're going to take that 4 and we're going to cut it into n equal pieces, right? 4 equal pieces in this case. So if I take the distance between the endpoints, 5 minus 1, and divide it by the number of rectangles, that will tell me how wide each one is. So with that same sort of idea, can you tell me how wide each one of these has to be? So what is the width of each of these? Okay, so how wide is the entire interval? How wide is the entire thing? So what's the distance from here to here?
X sub n.
Minus A.
X sub n minus a, or how about just b minus a?
Yeah, b
How
minus
about
a.
just b minus a? That's how wide that interval is. And then we want to divide that into how many equal pieces?
And
How many
Yes.
rectangles do we have?
Yeah, yeah.
N, right? N. That's the width of each one of those rectangles. Every single one of them is b minus a over n. So this is b minus a over n. So it's the height of the rectangle times the width of it. Understand? That's just the area of rectangle 1. What's the area of rectangle 2?
Would be f of x2 times b minus a over n.
Yeah, so the only difference between these two formulas is that instead of plugging in x sub 1 to get the height, we're going to plug in x sub 2 to get the height. The width is the same. So it's that, and then b minus a over n again. And then for the area of rectangle 3, we get f of x sub 3 times b minus a over n. And we do this for all the rectangles, right? Every single one of these. So what would the formula for the very last rectangle be? Area of rectangle n.
Yeah, f of x to the n times b
f of x
minus
sub n
times
and
b
then
minus a over
times
n.
b minus a over n. Okay. Now,
I was
if-
that was kind of what I was going for, but much cleaner.
yeah, this is the clean, there are other ways to do it, but this one is real nice because all of them are the same in every one. In every area of formula, we have the same width, right? Okay, so now if I wanted to come up with my estimate for the area, right? What I need to do now is add all these together, right? I need to add all these together. So my area estimate would be this. The area of this, remember, we're trying to estimate the area underneath this, right? So the area, we're saying the area would be approximately equal to the area of rectangle 1 plus the area of rectangle 2 plus the area of rectangle 3 plus, and then we keep doing that until we get to the area of rectangle n. Right? And that would be equal to, well, I could just start writing out each formula. F of x sub 1 times b minus a over n plus f of x sub 2 times b minus a over n plus f of x sub 3 times b minus a over n plus, and I keep doing that until I get to the very last one, f of x sub n times b minus a over n. Now, all of these have the same, all of these have something in common, don't they?
You're the b minus a over n.
And that means I can factor it out, right? I can factor that out. So I could write this way. F of x sub 1 plus f of x sub 2 plus f of x sub 3 plus dot, 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 until I get to f of x sub n. I could figure out what all of those added together are and then multiply that times b minus a over n. Still make sense? What the area is approximately equal to? Now, at this point, I'm going to do something, and I'm not quite sure how you're going to do with this because it'll depend on your college algebra. I'm now going to rewrite this like this. Sigma I equals 1 to n of f of x sub I, okay, times b minus a over n. Okay, so this all depends on your college algebra experience. If you've ever seen this Greek capital S sigma, this capital sigma is what we use. It's a shorthand for writing out repeated addition of terms. So the way this works is that you're going to start, this right here is your starting index. And then this right here is your ending index. And so what you do is this. You start with I being 1, and then you just you write this out, whatever this is, you replace I with 1. So if I write that out with I being 1, we get f of x sub 1 b minus a over n. Okay, so I replaced I with 1 and just wrote down what I wanted or what I got. Then you put a plus. And the reason you put a plus is because this is the sigma. Sigma is capital, the Greek capital letter S standing for sum, right? Sum. This is a shorthand notation for a sum. So
Yes.
I'm going to add to this. Now what I do is I let the index I change from 1 to 2. So now I rewrite this expression in the box with a 2 for I. Then I do it again, but now I let I be 3. And I continue to do this. And when do I stop?
You get
I'll
to
stop it at
f
n.
of x.
So
Yep.
my very last one will be dot, 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 f x sub n b minus a over n. Yeah, this is called a summation. Yes. The Greek letter S, this is sigma, which is a summation. All right, so do you all see that this is just a very nice, tight, compact way of writing out what we had on the previous page, right there. It's basically the compacted way of us writing this out. Instead of doing all that, we just have to write that right there. Much cleaner, much easier to see. Yes? Y'all okay with that? So that formula right there, that right there in that purplish box, if you had the time and you could sit there and start plugging in all these values to your function, then you would be able to get an approximate area. Now, the true area, okay, very important. Now I'm talking about the real area, not the approximate area. The true area is equal to, leave a space in front, is equal to that same summation with one little difference. One little difference. This is the formula that gives you the area of n rectangles. And what we said is, how many rectangles did we want?
Infinite.
Infinite,
An
yeah,
infinite. So what we're going to do is in front of this, we're going to put the limit as n goes to infinity of this sum. And that is the formula for the true area. If you could do it, right? If you could actually sit there and add forever, you can't, right? You can't do that. Now, in some calculus classes, what we do now, or what they do now, is they actually give you a specific function and they ask you to go find these sums. And it's very mechanical and it's a pain in the ass. And at the end, you get an approximation. Okay, that's not what I want you to do. What I want you to do is understand, I guess, when you look at that now, to realize what the pieces are. Okay, so like this is the height of the rectangle, right? That's how tall the rectangle is. This is the width of the rectangle, right? That's how wide it is. This is saying we're going to add up n of them. Okay, we're going to add up n of them. And then the limit is saying, then we're going to let the number of rectangles go to infinity. Understand? Taking the height times the width of each rectangle added up, and then let the number of rectangles go to infinity. Make sense? Like visually, you see where each piece, what each piece means, right?
Which one? I lost you after the first two pieces. I was trying to write it down.
Height, right? This is your height. This is your width. Height times width gives you area. And then this is adding them up. And this is letting the n go to infinity. That means the number of rectangles goes to infinity. Okay. Let's just put that on the back burner. Okay, let's put that on the back burner for now. We have that. We're going to move on to a different idea, and then we'll come back to this. So we have what's called, I've always had trouble with the word fundamental. Funde. A, E?
It's an A.
A? Yeah, okay, that's what my instinct wanted to say. Fundamental theorem of calculus. Now, I'm not just calling this the fundamental theorem of calculus just because I think it's really important. It is actually, that is the technical name for this. Okay, the fundamental theorem of calculus. And that I'm referring to all of calculus, not just Cal 1 or 2 or 3. This is the fundamental theorem of calculus. What this theorem is it creates a relationship between the derivative and antiderivative of a function. Okay, between a function and its antiderivative or the other way around. So let me write it down first in words, and then I'll show you the symbols that we use. Okay, fundamental, and then I want to put one more thing here. There's two versions of the fundamental theorem of calculus. The one I'm going to give you is called the evaluation theorem. Okay, so I'm giving you the evaluation version of this. There's two versions. Okay, so here's what it says just in words. It says the area under some function f on the interval AB is capital F of B minus capital F of A, where capital F is any antiderivative of little f, any antiderivative. Okay, so what is a theorem? In mathematics, a theorem is something that has been proven to be true. And I'm not going to prove this theorem to you, all right? You're going to have to take this on faith, unfortunately. But the great thing is that we can use it, all right? We're going to use it, and basically it gives us a way of very quickly and easily finding the area underneath the curve. Before this theorem, the only way to really do it was Riemann sums, okay? So if you wanted to try and estimate the area under a curve, you had to just start adding all these things together. And the more and more you had, the more accurate your answer was. Well, the fundamental theorem of calculus comes along and says, hey, wait, if you want that area, here's all you have to do. Find the antiderivative of this function, and then plug in the two endpoints into the antiderivative. So you're going to take that endpoint, plug it in here, subtract from it the other endpoint plugged into here. Subtract those two, and you're going to get a number, and that number is the area. Okay, that's like, whoa, that's crazy that that's the relationship, but that is the fundamental theorem. So how should we write this, right? This is where mathematicians said, how are we going to like write this? What symbols should we use to do this? And this is where the integral symbol came from. They said, okay, what we're basically doing is this, right? We're doing this. So let me copy this because I want you to really see this. They had the theorem. I want you to understand. They had the theorem, and they're like, what notation should we use for this? And they said, okay, well, this part, we'll just call that f of x. Okay, that's the height of the rectangle. And then this, right, that's how wide each one are, right? That's how wide each rectangle is. So that's how much x changes by, right? That's the change in x, but it's going to get really, really small. So let's call it dx for how wide the rectangle is. And then now you can see that this right here is the height. This is the width. And then what about this? This is not just a sum, it's a limit of a sum, right? So we don't want to use the Greek symbol, capital sigma, because it's not a sigma, it's a limit of a sigma. So let's use some other symbol. How about that symbol? Why not? It's an S, but it's like stretched out, okay? That symbol represents this limit of this sum. This represents the height of the function. This represents the width of the function. And that now, okay, so that right there, if we add an A and a B to the top and bottom of this symbol, that will be a place where we can notate what the interval is, okay? So we're going to start at A and stop at B. And then this should be equal to capital F of B minus capital F of A. That's basically your fundamental theorem of calculus. What I'm trying to, all of this crap that I did with the Riemann sums, all of this stuff was just to show you why we use this symbol and why it's f of x dx in here. The reason is because that's what the Riemann sum kind of motivates. Height, width, add them up, infinitely many of them. Say that again, height, width, add them, infinitely many of them, right? This is going to come up over and over and over in Cal 2, where you're going to be trying to figure out, I don't know, the volume of some three-dimensional object, and you're going to be like, okay, well, let's break it down to a bunch of slices. And then what we're going to do is we're going to find a formula for each slice, and then we're going to do add an infinite number of them. So we're going to do an integral. You'll see. Okay, let's see this in action. All right, you ready to do this? I'm going to, and we've actually done this. I showed you this before, but let's go back to this example. Remember the answer was 41.3? That was a true area under x squared between 1 and 5. So here's now how I would write this. I want you to do the area underneath the curve from 1 to 5 of x squared dx. So this right here, this, when I write that down, what I'm asking you to do is find the area under f of x equals x squared on the interval 1 to 5. So what is it that we're going to need to do that?
We need to find our antiderivative and then plug
Any
in.
antiderivative, right? Any
Yeah.
antiderivative will work. So let's find the antiderivative. What's the antiderivative of that function?
1 over 3x cubed,
1 over 3x cubed. Then plus any number, right? Plus any number.
right, plus c.
Plus c. But hold on. We can use any antiderivative, right? Any one that we want.
So,
Right.
so we could just pick a value?
Yeah. So why don't we do plus 0?
Okay, that works.
Let's just do that every time. For a definite integral, let's just do it every time. Let's just do plus 0. Because it just keeps things clean and easy. All right. The theorem says we can use any antiderivative, so let's use plus 0. So that's the specific antiderivative I'm going to use. Now, the theorem says that this will be equal to capital F evaluated at 5 minus capital F evaluated at 1, right? That's what the theorem says. So I need to figure out what's f of 5. I need to figure out what's f of 1. Okay, f of 5 is 1/3 times 5 cubed. That's 125 over 3. F of 1 is just 1/3. And now I come over here and I subtract those. So 125 over 3 minus 1/3 is 124 over 3, which is going to go in there 4 times 41.33 forever.
That's pretty close to what the graph was showing us.
Well, that is the exact answer. 41.33333 repeated is exact. You could also just leave it as 124 over 3, and that would be fine also. Okay, all right. Does that all make sense? I mean, this is pretty awesome theorem. I mean, again, I can remember vividly when I proved that theorem for the first time. As a math major, you have to go back and prove that theorem. You have to do what's called a delta epsilon proof, which is a precise mathematical proof. And I can remember when I did it, like it was yesterday. I actually did it. I'd been working on it. I was having trouble with it. Because remember I told you, and I don't know if I told everyone, but when you get to like theorem proving courses, like you can't go to tutors and get help anymore. Like you're on your own. So I'd been working on over like multiple days, and then I couldn't get through this one step, and I actually figured it out in a dream. Like as I was asleep, I figured it out. And that happened to me a lot in graduate school. Like I would dream it. And that was just because I was thinking it all the time. So I dreamt it. I woke up, I wrote it down, had the proof. I put on a whiteboard, and I went to go visit my parents. I hadn't seen them in a while. I put the whiteboard in the back of my car, went to my parents, and I opened the door and I went to go show my dad the proof. Like he didn't care, but you know, I just want to show him. And I opened it and their dog thought we were going to the park. So the dog jumps in the back of the car, big old white fluffy dog starts sitting on my whiteboard and like erases half the proof. And it was okay because it was all up here already. I didn't need it on the whiteboard anymore, but it was just funny that the dog just sitting there, you know, let's go, just erased all this work I did. So I remember it vividly when I proved it. Here, we're using it, okay? If I could prove it to you easily, I would, but I can't. It's too much to try and do in this class. So I would like now to do the same exact problem, but I'm going to introduce something new, okay? And it's just notation, and it makes our lives easier, okay? So let me show you the notation first, and then I'll show you how we use it. So if you're asked to do a definite integral, okay? So if you're ever asked to do this, okay? This means find the area under this function between A and B, right? That's what that means. Look under that curve, get the area between there. We know that to do this, we need to get the antiderivative and then plug in the two endpoints and subtract, right? That's what we need to do. So I'm going to put this new little intermediate step in here. My next line is going to be this, capital F of X, and then I'm going to put this bar next to it with A and B down here. Now, all this step is an opportunity for you to write down what the antiderivative is. Okay, instead of me going and figuring it out like scratch work on the side, I'm actually going to have it right here within my answer. I'll write the antiderivative down, I'll put the two endpoints, and then this bar is what we refer to as the evaluation bar. But simply said, all it really means is take B, plug it in, subtract A plugged into the antiderivative. So this is the new piece right here. So let me show you it with the example we just did. We go from 1 to 5, x squared dx. All right, first things first, I need an antiderivative, right? So the antiderivative is 1/3 x cubed plus any constant, but I'm going to use plus 0. Okay, so that's like a placeholder. That's just me thinking, okay, that's my antiderivative. Now I still need to evaluate it at these 2 points, 5 and 1. So now what I do is I say, okay, I'm going to take something here and subtract from it something, right? So this is this piece and this piece. So first I plug 5 into this. So 1/3 times 5 cubed, and then 1/3 times 1 cubed. So do you see how this just all flows real nice in one line instead of a bunch of like scattered work? That's the whole point of this notation. Start with what you're trying to do. Here's the antiderivative evaluation bar just to keep track of what we're going to plug in. And then plug in the 5, boom, subtract, plug in the 1, boom. And now just get your answer. 124/3. Okay, yeah? Your turn. I'm going to give you about 3 or 4 to do. Okay, here it is. So this is just practice. I want you to do the integral. So listen to the way I say this. I want the integral from 1 to 3 of, let's go x to the 3rd plus x plus 2 dx. Let's say that's problem number 1. Problem number 2. Integral from 0 to pi sine x dx. 3. Okay, I'm gonna give you about, I don't know, 10 minutes or so. See if you can get through these. And I will zoom out just a little bit so you can, or yeah, here, I'll move this down here. I'll just leave that right, just like that. Okay, enjoy. Okay. Well. Who are my volunteers?
I can go for the first one.
Okay, what do you got?
So I got that the antiderivative of x x cubed plus x plus 2 is 1/4 x to the 4th plus 1/2 x squared plus 2x, and then I put plus 0, which represents c.
Okay,
And then
you
I
don't
did,
have to have that. That's okay though.
Yeah.
And then.
and I
you
did the
put bar.
evaluate. Yeah, there you go. And 1 and 3. And then I evaluated it, and for big F B, I got 123/4.
123. Oh, you simplified it already?
Yes.
Okay, 123/4. And then minus,
And minus 11/4,
okay.
and then you get 28.
All right, anybody else get that?
I did the same stuff, but when I subtracted, oh my goodness, never mind. I took 1 away instead of 11.
Okay, anyone else get the same 28?
I got the same answer.
Yeah,
Me
okay.
too.
If we have a lot of people that got it, I think we can feel safe. All right, good. Any questions on that? No?
I'll go for the second one if you want.
Yeah, hold on. What I'm gonna do, x cubed plus x plus 2. So what I'm gonna do is graph this, x cubed plus x plus 2. And I'm gonna graph that between 1 and
3.
3. And there we go. So what we have done here is we have found the area. If you were to drop a line straight down here at 1, and then over here at 3 like this, like that. And we have determined that this area under this curve is exactly 28 units, which is weird that it's a nice number, but that's what it is. Okay.
Crazy.
All right, cool. All right, let's see. Next one. Cody, you're gonna do number 2.
Okay, so the antiderivative is going to be negative cosine x.
Okay.
So, and then I do the evaluation bar as 0 to pi. So I plug it in. Negative cosine of pi is going to give you -1. And then pi, and then negative cosine of pi is just going to give you 0. So it's,
So it'll be minus -1, right? Minus
so,
-1.
So
Okay.
you get just 1.
So you get 1. Okay. That's kind of weird. Because again, what we're doing is we're saying if you graph sine x, right? I always do that. Sine x, and you graph between 0 and pi. Oop. Graph it between 0 and pi, then this area is 1. Again, that's weird to me. The fact that that has an area of 1 is strange. It seems like it shouldn't be 1. It seems like it should be some weird number, but it's
I got
exactly.
a different answer
You got a different answer?
for 2,
Okay.
right?
You got 2?
No. Yes, for question 2, I got 2.
Okay, so what is cosine? So,
Because for me,
yeah,
when
you know what? Hold on, Cody. I think something's up here. What's
Yeah,
cosine of 0?
I got 2.
It's 1.
1.
Yeah, okay, sorry, I wasn't paying attention.
I think I didn't put the actual, the
This should be
second
-1.
negative.
Yeah, this should be -1. Cosine of 0 is 1, but then -1, but then you're going to subtract a -1, so it's +1. Okay, this should be 2.
Yeah, that's what I got.
Thank you. Yeah, thank you for pointing that out. Yeah. That area underneath that sine curve.
Yeah, I forgot the second negative.
This area right here is 2. Still weird that it's a nice number like that, right? Okay, who wants the third one?
I'll go for the third one.
Okay,
All right, so I took the antiderivative, and of course, any exponent to the x is just going to be the e to the x for the antiderivative.
and then we're gonna evaluate 0 to 1, right?
So you plug in e to the 1 minus e to the 0.
Which equals,
It's going to
E.
be 1.718.
yeah, so E minus 1 is what you get, and that's approximately 1.718, something like that. Good, that's right. And graphically, it's just the exponential function. And we're doing that between 0 and 1. There we go. So if you were to take this one and look here, then you're looking at an area of 1.718, something like that. Questions? All right, last one. Anyone get the last one?
I can do that one.
Okay, go ahead, Naja.
So if you use U substitution, you get the integral of 1 over U times du. which
Okay,
means-
good. Hold on, Naja. Let me just mention to everyone, this, to do the antiderivative, this one's going to take U substitution. So what I recommend you do, okay, is work this as an indefinite integral first. Okay, don't worry about the limits there, the limits. Don't worry about these numbers yet. Just hold off. Let's do this as, let's just find the antiderivative first. So Naja is going to use U substitution. You said U is equal to what?
1 plus x squared.
1 plus x squared, and that's because Naja realizes that the derivative of that is
2x.
2x, and then dx, right? Go ahead. So this is that. What does your new integral look like?
1 over U times du.
1 over u du. Good. And what is the antiderivative of 1 over u, Naja?
ln u.
ln of u. Now, I am going to put plus c here only because I'm doing this kind of as scratch work on the side. I am going to put plus c here. And now we replace u with 1 plus x squared. Good. Now we can continue the problem. This will be equal to that antiderivative we just found plus 0. So I'm not going to put anything, and then evaluate it from 0 to 2. So I've been doing this. I don't know if you've noticed this. I've been doing like 2 sets of parentheses. Every time I do this, I always put 2 sets of parentheses so I can figure out first what I get when I plug in 2. And then when I plug in 0. So Naja, what did you get when you did this?
I got 1.609.
Okay, so just natural log of 5?
Yes, sorry.
Right. No, it's okay.
Log of 5 minus natural log of 1.
Okay, yes, good. And the natural log of 1, everyone, that is 0. So our exact answer is natural log of 5, but the decimal, Naja, you said was what?
1.609.
Okay. So the area is about 1.609 for the function 2x over 1 plus x squared.
from 0 to
and
2.
on the interval
0 to 2.
0 to 1, is that what it was?
No. 0 to 2.
0 to 2.
Mhm.
There we go. So there's the curve. The area underneath it is that. Okay, good. Okay, I have one more for you to do. This is kind of a challenge problem. Hold on, let me see if. No, okay, no. Just thinking we can't do that one yet. Okay, yeah, we are gonna have to wait. All right, so Riemann sums, blah, 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 blah.
Just
Okay,
a
so
question, sir. Can we
yeah.
expect like at least one problem for the area under a curve on the test for the final?
Yes. Yeah. So when you have, this is the fundamental theorem of calculus that I presented, the evaluation theorem. Just to be clear on this, these right here, these numbers, A and B, these are called your limits of integration. Okay. That's this and this. This one is referred to as the upper limit of integration, and this is the lower limit of integration. And this is what's referred to as a definite integral. So the idea of a definite integral is that you are going to get a definite answer, right? A number, right? And that's going to represent your area. So there's a huge difference between an indefinite and definite, right? Indefinite, your answer is a family of functions. A definite, your answer is a number that represents area underneath the curve.
So basically indefinite, we're going to get some type of equation. Definite, we should get some kind of solid value.
Number, yeah.
Okay.
For now, later on, it is possible that you could get infinity, or it could not exist. It is possible, but for now. Okay, it's 2:26. Why don't we take a 10-minute break? We'll come back and see what else we want to talk about. And then we have the final exam review that we can talk about. So let's just take a little break.
Well, Jair, how are you feeling about the new stuff?
I feel pretty okay about it.
Yeah, I've noticed my whole problem throughout this entire class. I just have to slow down and stop messing up the simple arithmetic.
Yeah,
I shoot my own self in the foot.
that's something that I noticed too about myself. I had to like slow down a little bit.
Well, I don't know. I look at it and be like, oh, I know what to do. And then I just like think I rushed through it and I'm like, I've got it right. And then I find out, no, I took things for granted. Did his screen freeze on 12 seconds for anybody else? Well, no, I think he stopped it. Never mind. Second, I thought he was gone.
I'm here. Give me a second.
No problem, sir.
Okay. All right, so we're kind of at a point now where we have options here as to what to do. I mean, we can talk about the final, or I can continue doing, some substitution problems or more definite integrals, or I can even keep moving on with more material. So not that you'd be tested on, but just, I mean, it's kind of up to y'all. If you don't want to start talking about the final, we can do that. Really up
And
to
I'm
you.
open for that.
Okay, I sent out 2 reviews, right?
Yes,
So,
you did.
Let's see here. Let me just bring them up. I'll download them real quick because I don't know where I have them. All right. All right, so here's the first review. Well, this one's from spring 2018. And the other one is from, I believe, fall 2020. That's this one. So this is the one I sent you the solutions to. So anything that you'd like for me to talk about or go over, I'm happy to do.
For number 11 there, would we just ln both sides to pull the x out in front and have x ln sine of x?
Yes, for this
Okay.
one, because x appears both in the base and the exponent, and we're looking for the derivative, you would do logarithmic differentiation. That's correct.
12, we do the same thing, right? Logarithmic, just ln both and then ln of x plus 4. And then
Yeah,
you just
this
break it up
one-
even further.
Logarithmic, because you see that it has a bunch of things being divided and multiplied, things to powers. So logarithmic differentiation is the way to go there. Yeah.
13's, I'm just looking and thinking 13, that's infinity over 0. So have to do some algebra tricks to it.
Infinity over infinity.
Or infinity over, I thought with a ln of x, is it, well, no, that's not 0. Never mind. You're right. Infinity over infinity. So you could just do L'Hopital.
Mhm.
14, that's the one I missed on the test or something similar to that. How would we go about that one?
So that one, you have an indeterminate form, right? Let's see here. So if you take this limit, you're going to get 0 to the 0, right? And that is an indeterminate form from your limit summaries. 0 to the 0. right? Is
So-
bad. So we need to do something now. Unfortunately, because it's one of those forms, you know, you're going to have to call that limit y. So start off by calling it y. And then you bring the natural log in on both sides. And when you get to this step of taking the natural log of x to the x, you can pop the x out in front.
Mhm.
And then we could just drop it down with ln x over 1 over x,
So it's
right?
gonna be e to 0.
Yeah,
Okay.
so this goes to 0 and natural log of 0 goes to infinity, negative infinity. So now it looks like this, 0 times negative infinity. That's still an indeterminate form. So you drop one down. I think the x would be the one to drop. Leave the natural log there. Write that x is 1 over x on the bottom. And now you get infinity over infinity. Because 1 over 0 goes to infinity. And natural log of 0, we already said, goes to negative infinity. So at this point, you can do L'Hopital. And the derivative of the top is 1 over x. And the derivative of the bottom is negative 1 over x squared. That's because 1 over x is really x to the negative 1. And the derivative of that is negative 1 x to the negative 2, which is negative 1 over x squared. And then before you do anything else, clean it up algebraically. And it becomes negative x. If you just flip this fraction up, one of the x's cancels, and you have a negative down there still, so you get negative x. Now you just let x go to 0, and you just get 0 on the right-hand side. So you have natural log of y equals 0. So now you bring in e on both sides, and you get y is equal to e to the 0 is 1. So your answer is 1.
I always forget that last step where you get, ln of y is equal to 0 and then you e both sides. All right, well, thank you.
Mhm. So look at number 19, find the area under this curve. That's from today. It says find the area under that curve on that interval. So that means we want to set up a definite integral from 1 to e of natural log x over x dx. Anybody see how to do that one?
Yeah, something will be the ln x and then you have 1 over x dx you can get by taking the antiderivative of it.
You could rewrite this like this. And then you have to see that that integral we're going to need to do a u substitution on. Because I see something and I see its derivative. So I'll make a substitution, u is equal to natural log x. The derivative of that is 1 over x dx, which I have. So that integral just becomes u du. That antiderivative is 1/2 u squared plus a constant. And I replace u with natural log of x. So all of that was just to get the antiderivative. Do I need to address this or clarify anything here?
And we just set it the big F of e minus big F of 1 with that
Yeah,
formula.
so we're going to do the antiderivative here plus 0, evaluation bar 1 and e. And then we'll plug in to get our two answers. So we have to plug E in first. So 1/2 natural log of E squared, and then 1/2 natural log of 1 squared. What is natural log of E?
Isn't it just 1?
It's just 1.
Yeah, they cancel out.
So this just gives you 1/2 times 1, which is 1/2. And then natural log of 1 is 0. So that's just minus 0. So your answer is 1/2. By the way, let me just say something about this. There's a big difference between natural log of x squared and natural log of x squared. Those aren't the same thing.
Right, it's to be chain rule would be like 1 over x squared times 2x, wouldn't it?
Well, if you were taking the derivative, right? I'm saying if you were looking at those two expressions, the first expression, you could pull the 2 out in front and make this 2 natural log x. That is true. This one, you cannot pull that 2 out because the 2 here is acting on the x. This 2 is acting on the whole thing, the natural log. So the property of log says that if you have log of x to a power, then the power can come out natural log x, but the power there is on the x, not on the whole thing.
Oh, so that would be 2 ln x times 1 over x for the right side, right? For derivative.
If you wanted to take derivative of this now, you could. I'm not sure what you're asking me.
The right side, the ln x, then all squared, that would be 2 times ln x times the 1 over x for the derivative, right?
Yes, if you were asked to find the derivative of this, you'd bring the 2 out, 2 ln x, then times 1 over x.
So
This one would just be 2 times 1 over x.
just so I'm seeing it right. If we did the antiderivative of the ln x, all that squared, then it would be 1 over 3 ln x to the third
No.
times the inside.
Mm-mm.
Mm-mm.
Yeah, no, it wouldn't work out that way. You're saying if we had this and we wanted the antiderivative, that would not be equal to 1/3 natural log of x to the third plus c. That would not be right. Because if you took derivative of this, the 3 would come out, cancel out. You'd have natural log of x squared. That would be correct. But then chain rule, you'd have a 1 over x. And you can't put an x out in front. Like you might think, oh, okay, just put an x out here to take care of that x that comes out from the chain rule. But now when you take derivative, you have a product rule. So it becomes completely different. So this, I would say, is an open question. That's not something we can do at this point. We as in us in this class right now.
We just haven't learned how yet.
Yeah, we don't have a method for that yet. In fact, I'm not even sure that it can be done with all the methods.
I thought it looked so simple, but it's apparent it's much more complicated, I guess, than I
Yes.
originally thought.
It is. You could probably break it up. Yeah, it can be done. It can be done, just can't be done with anything we're doing.
I was gonna say, I'll take your word for it because I didn't follow that, so.
Okay, other reviews. Okay, so look, I'm gonna say, look, at this point, what time is it? It's 2:50. So at this point, if you have, questions you want us to hang out and talk, we can talk review. If you feel like you're good to go, there's no new material. The final's on Thursday. Just make sure you show up on time and have your camera all ready to go. Formulas ready to go. And your reference sheet, if you're going to do that, make sure it's ready to go, and then we will grind it out. Okay.
Could we go over number 8 on there, that related rates problem? I just want to make sure I did it right,
Yeah.
I guess, since no one else is saying anything.
Yeah. So I'm saying if you're happy, you're welcome to leave. You're not going to offend me. And then after you leave, I'll give everyone bonus question. No, I'm kidding.
I want to make the joke and say he's really not, but that discourages me from leaving as well.
No, I wouldn't do that. I wouldn't do that. This one,
Yes, sir.
the volume of a cube is increasing at a constant rate of 20 cubic centimeters per second.
Yeah.
How fast is the edge of the cube increasing when the length is 10 centimeters? Okay. So this is a related rate problem. So we have the general picture, and you can have that sheet during the test if you want to print out a few blank ones. The instant in time, what you're given, what you want, what the equation is going to be, and what your implicit is going to be, and then your work and your answer. Okay, so the general picture is we have a cube, three-dimensional, and it's growing so that its volume is increasing at a constant rate. Okay, so generally it's a cube. So this is x, x, and x, three sides, x, 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 it's a cube. We know that at the given time, we're talking about the instant time, the cube looks like this, where this is 10, 10, and 10 for centimeters, right? We're given how fast the volume is changing. So we're given that the change in volume with respect to time is 20 cubic centimeters every second. We want how fast the edge is increasing. So I want to know how fast x is changing with respect to time at exactly the moment that x is 10 centimeters. We need an equation that relates the volume to x, and that's a pretty straightforward one. Volume is x cubed. So now I do implicit differentiation of this. So with respect to time on both sides, the derivative of v with respect to t is dv dt. The derivative of x cubed with respect to t is 3x squared dx dt. Chain rule.
Right.
And now, let's see, this is going to turn into 20. X is going to turn into 10. And dx dt is what I'm looking for. So this is going to be 20 equals 300 dx dt. Divide both sides by 300, you just get 2 over 30 is dx dt.
For my approximate value of that, I got, where did it go? 0.0666 cubic centimeters cubed a second. Okay, yeah, I did it right.
And this would be centimeters per second.
Oh, we wouldn't cubic. Oh, no, because it's not the volume itself, right?
Yeah, it's the length, right? dx dt, x is the measurement of the one side. So you're saying how fast is that side increasing?
Yeah.
0.066 centimeters every second at that instant.
Oh yeah, sir, real quick. Does the answer have to be in decimal form or can it be in fractal form?
Either one. Either one. Just don't round that to 0.1. You
Gotcha.
go at least 2 or 3 decimal places if you're going to do a decimal.
Oh, what about the homework thing you were talking about, showing the stuff, the work and all that?
Oh yeah, I'm
jazz?
glad you brought that up. Yeah, so the homework,
It's like I just made enemies.
we're gonna probably do that right at the beginning of the test. Remember, at the beginning of the semester, I said that I would do a homework where you keep all your homework in a folder, and then at the end of the semester, I'll have you hold your work up to the camera and kind of just thumb through it. We'll do that at the beginning of the test. Take us 5 minutes. Yeah, if you got a big old thing, that's okay. Just kind of, yeah. All right.
Yeah, I've got notebooks, I've got papers that are stapled together, etc. Oh, it's everywhere. I can find.
Yeah, I
it,
just
think.
ripped them out when I did them and just had them in a thing. I was like, all right, well,
Yeah,
it's the only way for me to like keep them together.
I just got tired of ripping out like page after page, and then my OCD, I have to like make sure I perfectly get that part that it connects to the binder with, and it's oh, it's terrible.
think at a certain point, I just started to write it like digitally, so I have to end up printing it at the end. But because I use so much
If you have it
paper.
digitally, that's okay. You can show me your digital. Just
So we'll just like have our binder open and then we'll just like skim through our homeworks.
yeah, yeah. I mean, this is kind of a free grade here. I mean, it's not. I think if I remember correctly, let me go back to the syllabus because did we have a homework grade?
You know, you said you were gonna add it. Speaking of which, I don't know if I've got my quiz 3 grade yet.
No, you haven't. People are already mad at me about that.
Oh, I
So,
wasn't
yeah,
mad. I just
so
making
your-
sure.
Your homework and quizzes is 15%. Okay. So the homework, I have to count something. So that's what you're gonna flip through, right? And then you have a couple of quizzes I need to get those graded. I'm falling behind. I'll get it done because trust me, I'm starting finals tomorrow, and the last thing I want to do is go into finals with stuff to grade from the past. So I'll get it done.
Is
I
that
just
this,
wanted to, oh, go ahead. Sorry,
with
John.
that bonus question you had us do
Mhm.
for extra points? Okay.
Yeah.
Did you ever
there's a quiz and a
decide how,
bonus, both of them.
did you ever decide how much that's going to be worth?
I was going to look to see how many people submitted it and how many people got it right. So normally with bonuses, they're worth more if fewer people do them. Like, if you know what I'm saying? Like if everybody does it, everyone does it correctly, then it wasn't quite hard enough for a bonus. So it'll be worth something, just not as much as if only 3 people got it right.
Gotcha. Thank you.
Mhm. All right, anything else on the review?
No, I think I've asked what I needed help with. Yeah, I talked to you about the concave up, concave down earlier, so.
So the test is gonna be over what we've been studying for the past few weeks, or like like throughout the whole summer.
Well, I think the review gives you a good indication of what to expect. The only thing I would say is towards the end, I wasn't sure how far we would get. So the review has 2, these are both substitution problems, 5.5, but we now could do definite integral. So I could put numbers on these now, right?
You could, yeah.
And that would change a little bit of the work, but you'd still have to find the antiderivative, like no matter what. So I would just expect that maybe you see a definite, kind of like the one we just did.
So expect like an
Yeah,
indefinite and a definite.
The area problem right here, that's a definite integral.
So expect one of each, like one indefinite, one definite. Something like that. Fair enough, fair enough. All right, what we
Expect-
talked about earlier.
Yeah, I'm not gonna say one of each or, yeah, I mean,
You can't blame me for trying,
Yeah.
shoot that shot.
yeah. All right.
Well, I keep feeling like I've got to keep asking questions because it just goes dead silent. So,
You don't have to.
well, I know, but I feel awkward and I'm not even the one that's not talking. I feel awkward when it gets quiet.
It doesn't bother me. I just want to make sure everybody has an opportunity to ask any questions right now. I mean, if you haven't done the reviews, I understand that, you need some time to know what you need to ask, but we're here. I can do examples or whatever of anything you want, but I've kind of run out of material unless we want to get into, further into Cal 2. So,
Tomorrow's your last office hours, right? You don't have any on Thursday.
yeah, tomorrow's my last one because Thursday, I have finals starting at 9 a.m. and ending at 10 p.m. So all day. Yeah.
Oof.
It'll be a long day.
So for this review for number 3, what like the okay, yeah, isn't that one the one where we have to do like lim f of x minus f of a as
Yes.
x versus a?
Yes, that I'm glad you asked that. That's important because people will do this problem and they'll get major points taken off because they're not reading the instructions. So it says to use the limit definition. Okay, So people will look at this, say, oh, they want the derivative of that. They just do 4x minus 3 and they move on. And then they get like 9 points taken off because they didn't use the limit definition. So on your reference sheet, you probably want to write down, the derivative formula from when we were using limits. There were 2 of them, right? Limit h goes to 0, f of x plus h.
Yeah, that's the one I used for
f
this
of x
problem.
over h. Yeah, that's the one that I like. And then there's also the derivative at a, which is the limit x approaches a, f of x minus f of a over x minus a. You can use either one. You just have to remember that one of them gives you the derivative at x, the other one's at a. So if you use this formula, you're going to get an answer 4a minus 3. If you use this formula, you're going to get 4x minus 3 when you go through all the work.
So for the reference sheet, it can be front and back, right?
Yep.
Okay. Thank you.
And we're going to scan that in when we submit, right, too?
Mhm.
And the only thing really barred is just no worked out problems.
Yeah, just don't work anything out.
Can you go over one of the examples that we went over in class today?
Yeah, which one?
Number 4. It was a defined interval. Yeah,
This
that
one?
one. Yes.
Okay, so let me see here. Where was it? Here it is, right here, right? So you're trying to find the antiderivative of 2x over 1 plus x squared. And unfortunately, you can't do anything easy with that. Like, you can't just do the antiderivative of each one of these separately. You can't do that because you have a big fraction, right? You can only do it if you have x's to powers separated by addition and subtraction. So that means we have to do something else. So the only thing we have other than basic power rule is substitution. So I rewrote the problem, and then this is the part I think that you have to get comfortable with, is this idea of looking for something and its derivative. So Naja had done this problem, and she had noticed that if you take 1 plus x squared, the derivative of that is 2x dx. Are you okay with that, Justin?
Yes, sir.
Okay, and then we just rewrite the problem. So when we rewrite this, one way you can look at this is 1 over 1 plus x squared times 2x dx. So you can slide that 2x off to the side with the dx, and that way it matches exactly right here. So all of that gets replaced with the du, and then the bottom of this one gets replaced with the u. Is that still okay, Justin?
Yes.
And then now you just need to know what the antiderivative of 1 over u is. That's the special case. That's the one that we have to kind of remember. The antiderivative 1 over u is the natural log of the absolute value of u.
Okay. That's where I got hung up.
Oh, this part right here, from here to here?
Yes, sir.
Yeah, so let's just say it would have been 1 over u squared instead, right?
Mhm.
Then you would not have done this. You would have done, okay, well, that's just u to the negative 2 du, right? So you'd bring that up as a negative power, and then you use your power rule, which would say it would be u to the negative 1 because we're adding 1 to that power. And then we have to do the reciprocal out here of negative 1, which is 1 over negative 1 or negative 1 over 1, however you want to look at it. And then that would be negative u to the negative 1 plus c, which is the same as negative 1 over u plus c. You see the difference between those two?
Yes, I do. I
Okay.
think I was trying to do it with the power rule one, and I knew I couldn't do it correctly because it'd just be a 0.
Yeah, you get a 0. And what happens is in that front piece where you have to do the reciprocal, you get undefined and you get division by 0. And it's, so yeah, that is the special case. Just be on the lookout for it.
Thank you.
Mhm. All right. So I've got something fun. How about this? 1 + 1 is equal to 1. Have you all ever seen this before?
Something like it.
Yeah, so I'm gonna try and prove that this is true, okay? I'm trying to convince you that 1 + 1 is equal to 1. All right, so here's what I'm gonna do. I'm gonna let A be equal to 1 and B be equal to 1. All right? So I'm just gonna let everyone know right now, A is 1 and B is 1. Trying to remember how to do this. Do you agree with this then? Then A equals B. I'll agree with that.
See, yes, I feel like this is gonna be one of those things where conceptually or technically it will make sense, but my mind will just say, this is BS. 1 + 1 is 2, damn it.
Yeah, so let's see what happens. Okay, so next thing I'm gonna do is I'm gonna multiply both sides by A. Okay, so now A squared equals AB. Do you agree with that? Just multiply both sides by A. Yes?
Hesitantly.
Okay, why? Okay, well, I mean, this is the thing. If you hesitate, then that's,
Well, no, I agree with your stuff. I'm just still trying to get over how the whole base concept is all. I'm sorry.
okay. You agree that A is B. If I tell you A is 1 and B is 1, then A is B.
Yeah.
Okay, and I can multiply both sides by A and get A squared would then have to be equal to AB.
Mm-hmm.
Okay, now what I'm gonna do is I'm gonna subtract something from both sides. So if I take A squared, I can subtract B squared from both sides. Because we know that you're allowed to, right? You're allowed to take away something as long as it's the same on both sides, right? You can add or subtract on both sides of an equation. You agree with that?
Mm-hmm.
Okay, the left side is a difference of squares. You see that? In the right side, I can factor out a B. Difference of squares, factor a B. Now they both have an A minus B, right, on both sides. So I can cancel out A minus B and get A plus B is what's left on the left equals B. But what was A?
A is 1.
Plus B
is 1
equals 1. 1 plus 1 is 1, or 2 is 1. So go to your bank and see if they'll turn that 1 into a 2 for you. Turn all of your 1s into 2s.
I suspect I might meet more resistance than I've found myself resisting
Yeah.
this.
Okay, so this obviously is not right. Okay, but where's the problem? Where's the mistake? Where's the incorrect thing?
A plus B can equal B.
A plus B, well, yeah, I agree with that, but I'm saying you were supposed to follow me logically from step to step, right?
Mm-hmm.
Everyone agreed that A was B. Everyone agreed I could multiply both sides by A. Everyone agreed I could subtract B squared. Everyone agreed I could factor. Everyone agreed I could cancel the factors on both sides and then get to the last line. So something in there is wrong.
But wait, don't you have to you have to have both sides of your equation be equal. So, well, no, take away add on the other side wouldn't be right. Mm.
Okay, so let's go from the very first step. Okay, the very first step, A is equal to B. We're all good with that, yes? 1 is equal to 1. Yeah, okay, now the next step, what I did was I multiplied both sides by A, right? Okay, are you allowed to multiply both sides of an equation by a number? If you have an equation, can you multiply both sides by a number?
Yeah.
Yes. Any number?
1.
Any number.
1 would be fine.
As long as
You
it's
multiply both
by the
sides by
same,
2?
right? Yeah.
First line's
Okay.
not by
Both sides
0.
by 3, both sides by
Yeah.
4, any number?
No, you can't do 0 or
Can't
infinity,
do
I would
0.
say.
Yeah.
Because if you do 0, it just kills both sides and you get 0 equals 0. It just wipes out the equation, right?
Mhm.
But I multiplied by a, didn't I? And a was what?
1.
1. Okay, so that step's legitimate. I multiplied both sides by a non-zero number. Okay, next step. I subtracted b squared on both sides. If you have an equation, can you subtract any number from both sides?
Yeah.
Yes.
Yes, any number. It doesn't matter what it is. Okay, you can subtract.
I think I know what it is. It the
next?
next step that's screwed up? I think it's the next
The
step.
factoring step.
Yeah, because you can't. Or no,
Go ahead.
not that one. The one after it.
Okay,
That one.
this one. This
Yeah.
canceling. What's wrong with that?
Yeah, because I'm trying to see because it's like this is the part where you're getting rid of one. You're kind of removing the two. You're creating an equation where 2 is equal to 1 essentially. So I was trying to look around this area. You can't. You can't cancel the.
You can divide both sides of the
Let me,
equation
let me
by
give you.
something.
Let me ask you to look at this equation right here. I want you to look at this equation right here. 4x equals x. Okay. They both have x on both sides, right? So because they both have x's, I can cancel the x on both sides. Yes or no?
No.
Why not?
Because it's multiplication. Or because you would get.
X is a variable.
But we leave behind 4 is equal to 1, which doesn't work.
What is the canceling? What are you actually doing? When you're canceling it from both sides, what are you technically doing?
Dividing.
Dividing both sides by what?
By x.
By x. So I'm dividing here by x and I'm dividing by x, right? And then the x's go away, the x's go away, and then you get 4 equals 1, right?
Mm-hmm.
So
Which,
a minus
which
b
isn't
is
true.
0.
But the division, what did I divide by? X. Can you always divide both sides of an equation by any number? If you have an equation, can I divide both sides by any number?
Not by 0.
Not by 0.
Yeah.
But what's a minus b?
0.
It's 0. So what I really did here, and I snuck it by you, is at this step right here, I divided both sides by a minus b and canceled it, which is only allowed if a minus b isn't 0, but a minus b is 0. So I divided both sides by 0. And that's why I have that incorrect result.
So simple. Oh.
So this leads me to something else. This is something that may come up in your math life later that I see a lot of students do wrong. Let's say we have this equation, 4x squared equals x. And I want to solve for x. What students will do is they'll divide both sides by x. Okay, so if I do that, I'm going to get 4x equals 1. Y'all see that? And if I divide both sides by 4, I get x is a fourth. And that's the answer I get. Okay, so let's look at the original problem over here. That was the original problem. I did division by x on both sides, and I got x is a fourth. Is 1/4 an answer? So let's try it. 4 times 1/4 squared, does that equal 1/4? So 1/4 squared is 1/16, right? And 4 times 1/16 is 1/4. And 1/4 does equal 1/4. So this is true, right? So by doing this, dividing both sides by x, I got the correct answer, didn't I? But is it the only answer?
No, wouldn't it be plus or minus because it's going to be a square?
No, not plus or minus. Christian, you're saying 0, right?
Yeah.
0 is a solution. Just look at it. Plug 0 in for x, right?
Oh, you're right. Never mind.
Right? 0 is a solution, right? Why did we not get that solution? Why are we missing that solution? The only solution we have is 1/4. Why are we missing it?
We didn't factor out an x from the 4x squared.
We divided by x, right?
Mm-hmm.
And when you divide by x, you better promise me x isn't 0. So when you divided by X, you actually had a little asterisk. There should have been a little star here, you know, the fine print, and it should have said X can't be 0. Like you eliminated one of your own solutions by doing this. So what I remind my students is that whenever you have an equation, you always have to be careful to not divide by a variable, because you don't have control over that variable and you eliminate possible answers. So the correct way to do this is to move everything to one side of the equation. Everything to one side, factor, and then set each factor equal to 0. And in that case, you will get both answers. So the moral of the story here with both of these is you have to be extremely careful when you're canceling things on both sides of an equation when they're not numbers. When they're variable expressions, you better pay attention to what they are.
I mean, in a way, sir, I don't know if anybody left. Well, some people left, and you kind of did give a bonus question. I mean, it's not points or anything, but this is future material that, you know, could be helpful.
This is bonus material. This is not a bonus question. It's bonus material.
Well, you did pose it as a question.
It's going to be on the test.
Yeah.
Gosh. Huh.
Yeah, I should put that on the test, right? Prove 1 + 1 is 1. Yeah.
I'd be okay with that.
I bet anybody that's not in here automatically thinks it's a curve and says it doesn't and moves on. Just saying.
Have I shown y'all this one? Have I shown y'all that when you take 1 + 2 + 3 + 4 forever, or not forever, and then you stop somewhere like at n, that there's a formula for this? Did I tell y'all that story?
Was it at the very beginning? Or not very
don't
beginning,
know.
but pretty close to the beginning? I think you might have.
I told you about the kid, and you'll remember if I tell you the story. The kid that was in kindergarten. Did I tell y'all this story?
I don't think
It's
so.
not.
I'll share
No,
this
it's not
with you.
ringing a bell.
I don't think so.
This is a myth, okay? Nobody knows if this is true. There's a mathematician, very famous mathematician named Gauss. Last name Gauss. I think first name is Frederick Gauss. Let's look him up. Frederick Gauss. Gauss. Is it Gauss?
Yeah, Carl Friedrich Gauss.
Carl Gauss. Okay, so the story goes like this. He's in first grade or kindergarten back in the 1800s. He goes to school, and the teacher goes up and gives the kids this problem. The teacher says, okay, what's 1 + 2 + 3? So the students, you know, work it out, raise their hand or whatever. They say, you know, of course the answer is 6, right? And then the teacher says, okay, what's 1 + 2 + 3 + 4? And they go, okay, well, that's 10, right? So the teacher then goes, what's 1 + 2 + 3 + 4? Keep doing that until you get to 100. Now, this is before calculators. This is just by hand, right? So the story is that the teacher just didn't want to deal with the kids that day and was giving them like busy work, right? And so he gave the kids the problem, thought it would keep them busy for, you know, 20, 30 minutes maybe. And so he goes and sits down at his desk, and then like within a few minutes, Gauss, they used to write not on paper in classes. They all had little like chalkboards, little slate boards, and they would write. And anytime that they were done with something, they would turn their board over and they would cross their arms and sit there very politely and quietly, because back then they had respect and all that other manners and shit like that. So so the teacher looks out, sees Gauss flip his little board over and sit there, and Gauss is just sitting there, and the teacher's just kind of like, what? So it goes to Gauss, turns his slate over, and Gauss has written n times n + 1 divided by 2. Right? That's what Gauss has written. Now, this formula at the time was known, okay? Gauss was not the person to come up with this, all right? So let me tell you what the formula is first. The formula adds up the first n numbers. So if you stop at n, then all you have to do is plug where you're stopping in to this formula and it'll kick out the answer. So like, for example, we stopped on the first one, we stopped at 3, right? So if you put 3 here and then 3 plus 1, what's 3 plus 1?
4.
4. So 3 times 4,
12.
12. Divide by 2, you get
6.
6. Okay, here we stop at 4. 4 times
5 is 20, divided by 2 is 10.
10. Okay. If you plug in 100, it'll be 100 times 101, divide by 2. That'll be what you get if you add up the first 100 numbers. Quick, simple formula. Okay. So teacher turns over thing, sees the formula. And like I said, it was a known formula, right? So the teacher got upset and said, you know, who showed you that? And Gauss was like, you know, nobody showed me that. I just came up with that formula. And the teacher was like, I don't believe you. And took him to the principal or whatever to get in trouble or whatever. So Gauss had to go explain how he came up with the formula. All right. He had to justify where this came from. All right. So you ready? I'm gonna show this to you and let's see if you can follow it. All right. So Gauss said, all right, you wanted me to add up the first 100 numbers, right? So Gauss said, I'm going to call this, I'll call it X. Okay. I don't know what he called it, but he said, that's X, right? Want to add up the first 100 numbers. So Gauss said, well, what I also know about X is that it's addition, right? So the way you add numbers doesn't matter. The order doesn't matter. So if you wanted to, you could write it backwards. And it would give you the same exact sum, wouldn't it? Your last number would be 1, the one before 2, the one before 3, the one before 4, right? This would be the exact same answer. Yes? And then Gauss said, well, that means that if I take these two and add them together, X plus X would give me 2 X's. And watch what happens here. If you add straight down, what's 1 plus 100?
101.
101. Plus, what's 2 plus 99?
101.
What's 3 plus 98?
101.
All the way down, right? All the way down. All the way till you get to your last one. Your last one will also be 101, right? And Gauss said, okay, how many 101s do I have? How many of them are there? So we can count them. There's 1, there's 2, there's 3. How many of them are there?
100.
100 of them, right?
Mhm.
There's 100 of them. So Gauss said, all right, 2x is 100 101s, right? It's 100 101s, but that's twice as much as what I need. So I need to divide that by 2. And that will be what X is. Does that make sense? Okay. Now, I lied to you. This is not what Gauss did. Okay, I only did that because I need to lead you into this. All right. Gauss did it this way. Gauss said, you want to, I'm going to try and add up the first, not 100 numbers, the first n numbers, right? So what's the number right before n?
N minus 1.
Yeah, whatever n is, take 1 away. And what's the number right before that one?
Minus 2.
N minus 2. Do y'all understand? So Gauss said, that's X, the first n numbers added together. And then he rearranged them. So he flipped them over and did n here, n minus 1 here, n minus 2 here, plus until he got all the way to the end, which would be 1, 2, and 3 this way. And then he added straight down again. So he did X and X, that's 2X. And then here's the cool part. This and this together is what?
N plus 1.
N plus 1. And then what would these two together be?
N plus 1 as well.
Minus 1 plus 2 would be N plus 1 again, wouldn't it?
Mhm.
So it's going to add another N plus 1. And that's going to continue to happen the whole way down until you get to the very end. You'll have N plus 1 again. How many N plus 1s do you have?
N.
N of them, right? You have
Mhm.
N of them. So 2x is N plus 1s. But that's twice as much, right? So divide both sides by 2. So if you were able to follow that, it's doable, right? I mean, that is.
What
if you
grade
followed
was
it-
he in when he did this?
Yeah, so that's what I was about to say is, so the fact that most of us can kind of, I see that, that's pretty good. That's one thing. To come up with this when you're in first grade,
Holy.
that's genius, right? That's genius. And that's why Gauss was a genius. Okay,
Cheat
he's
code.
doing that at that level, at that grade level, he's doing that. So, in college algebra, you learn about solving systems of equations,
Mhm.
right? Like if you want to solve x plus y plus z equals 4, and another one, 3 equations, 3 unknowns, something like that. And you're taught the method of elimination, right? Elimination. Well, if you look up Gauss on the internet, when you type in Gauss, one of the first things you're going to see there is Gaussian elimination. And Gaussian elimination is named after Gauss because he's the one who actually came up with it.
In the
All
first
right?
grade,
His method is
apparently.
named after Gauss. All right. So Gauss did so many things in math. It's pretty unbelievable the amount of stuff that he did.
Didn't he do like, I know he did something with geometry, and then, but wasn't he into like astronomy too of some sort? Something like that?
Could have been, I don't know. I mean, these geniuses had their hands in a lot of different things. But anyway, I like that because, again, it illustrates how something that seems like it could be very complex can become actually pretty easy if you approach it the right way. Another approach to that same problem that I like is if you look at 1 plus 2 plus 3 all the way out to n, you can do it visually with boxes. So if I do a box here, that's 1 box. If I stack 2 like that, that's 2 boxes. There's 3 boxes. There's 4 boxes, right? So if I keep doing this, let's say at the very end, I've stacked n boxes at the end, okay? So I've got this like pyramid thing going up like this. Understand? Take a copy of that. So copy that, paste it, and rotate it. Okay, so I'm going to do an exact copy of that, but put it upside down. Then how tall is this now?
N.
N goes from here to here. I stacked it on top of that other.
Oh, N plus 1 then.
That's n plus 1, right? And this from here to here is
It's
n.
N.
So if you look at the area of the whole thing, right? The area of the whole thing would be n times n plus 1. So if I wanted to know the area of just this black part, which is actually 1 plus 2 plus 3 plus 4 plus 5 all the way to n, it would be half of that. It's just another way of doing the same thing.
Off topic, but I've been wanting to ask you about this because I saw the episode along. I think it wasn't How It's Made, but have you ever had any experience with mathematics? And I believe it's the Hagoromo chalk craze. Like that perfect Japanese chalk that apparently many high-level mathematicians believe only the best of theorems are wrote or written out of or something like that. I just was curious if it was actually,
The what?
it's like called Hagoromo chalk or something like that. It's some chalk from Japan that they don't make anymore that I saw on TV, like all the high level mathematicians have just stockpiles of it for some reason. And I was curious
Oh.
if you'd known about it, but
No,
I don't
I mean, I can only say that I did a majority of the math that I did in my academic life with chalk. We didn't go to dry erase markers until computers became prevalent. I mean, that's really why we went away from chalk, is because when you have a lot of computers in a room, chalk dust gets into the internal components of the computers. Expo markers are much more expensive. Chalk is cheap, but I miss chalk because I'd be done after a day of doing math and I would be covered in chalk and I'd feel like I just, like I was, doing something.
here's an article on what I was talking about if anyone's interested. I'm sure it probably sounded a little wild. I'm just randomly asking about chalk.
I've heard of what you're talking about.
It's like there's some people out there that really believe that if you don't have this chalk, you're not going to get your theorem right.
Yeah, that's,
I was mostly just curious. I doubt that the superstition's actually real. It's all mental. I was just
Yeah.
curious if it's actually as much of a, if you knew if it was as much of a cult-like thing going on as it really presents itself to be. But
I think that most pure mathematicians prefer chalk. I will say that. Now, this particular brand, I don't know. I mean, whatever. I mean, you can just tell. Look at their hands, right? I mean, it's almost like you got like signs of doing work, rather than a dry erase board, which you get colors, but
I just always found like the manual input of like forcing the chalk in to get a nice solid line was a little bit more satisfying maybe than the expo markers, but writing really nice wide script with expo markers is pretty satisfying as well. So I guess positives in both.
there's some nostalgia. For me, it's the nostalgia of the chalk.
Wait, so that whiteboard that you had in the back of your car, was that a chalkboard or like actual like expo chalk?
It was
like
an
actual-
expo. It was
Okay.
an expo. Yeah.
I did also like that story because it made me feel good. That at least I'm not the only one that wants to go show my dad some crazy math that I figured out. So
Yeah.
mostly I just wanted, if you want the truth, I was being petty. I wanted to rub in the fact that like, yeah, I'm doing this and you didn't do this in college. Yeah, derivatives.
Yeah. No, I don't know why I wanted to show it. Maybe just I told y'all, I had a history of not doing well. So it was kind of like, I was proud of myself. So. All right. Well, God, it's only 3:30. Our classes actually went this long.
Yep.
Damn.
It was a long semester.
That was a long class, but it's different when I'm the one talking. I understand. When you're on that end, it's a little different, but. All right, has anyone changed your mind about asking any questions?
Me.
Okay, what do you have?
Can you go over the problem 2 from fall 2020 review?
Yeah, this is a beast of a problem here. Well, no, wait, no. The first one is kind of messy. This one is not so bad, but. Okay, so one of the things I'll say on this is that you want to be paying attention again to what the instructions are asking you to do, right? Asking you to find the equation of the tangent line, right? So that means right away you should be thinking, I'm going to be using the point slope formula to find the equation of the tangent line. You're also given a point, so you already know here what x1 is, and you already know what x2 is. Y1 is. So right now, just out of the gates, you know that this is y plus 2 equals some slope times x minus 0. Like you already have that much of the equation. The only thing you don't have is the derivative. And when I say the derivative, I mean you want the derivative right? You want basically y prime at x equals 0. And so what I saw on the test, a lot of students were doing was that they were doing everything, they were getting the derivative, they were doing the equation, but here for m, they actually put the derivative in there, not the derivative evaluated at a specific point. So instead of putting a number there, they're putting like an entire like expression, which is incorrect. So we need the slope at the point x equals 0, y equals -2. Okay, so we need the derivative. So this is an implicit equation. We can't solve it for y. So I'm going to use implicit differentiation. So Daniela, there's two ways to do this. You can leave it the way it is and treat these like products and do a product rule here and a product rule here. Or before you begin the problem, you can actually distribute this through and get y to the 4th minus 4y squared equals x to the 4th minus 5x squared. That's what I would do if I were you, but you could do the product rule. So Danielle, is it okay if I continue with this version?
Yes.
Okay, so derivative time. So the derivative, I just moved from left to right here because I have just subtractions here. So the derivative with respect to x of y to the 4th will be 4y cubed times dy dx. If you don't want to use dy dx, you can use y prime there instead. It's up to you. Minus now the derivative of this, which will be 8y times, again, dy dx. Daniela, do you understand the dy dx, the chain rule happening?
Yeah.
Okay, now I'm done with the left side, go to the right side. Now these are going to be regular old derivatives because I'm differentiating with respect to x. So when I do chain rule, the 4 comes down x cubed, then the derivative of x with respect to x would be a 1. So there is a 1 here, you don't need to write it, but there is a 1 there, dx dx. Then minus 10x, so the 2 comes out, hits the -5, and then the derivative of x again is a 1 back here. So there you go. Okay. Now, because we are actually finding the equation of the tangent line at a specific point, I do not need to get dy dx by itself on one side of the equation. I don't need to do that at this point. What I can do is replace all the x's with zeros and all the y's with -2. Okay, so let's do that. I will have 4 times -2 cubed times dy dx minus 8 times -2 dy dx equals, now on the right side, I'm plugging in 0 for x, so everything goes away. We just have 0. Now, -2 cubed is -8, and I hit that with the 4, I get -32 dy dx plus 16 dy dx equals 0. Those are the same, right? Those are both a number in front of dy dx. So I put those together, I get -16 dy dx equals 0. And then I divide both sides by -16. And I get dy dx equals 0. Now, this number is our slope. So when I come back up here to this equation, I had y plus 2 equals m times x minus 0. But my m I just found was 0. And that kills off everything on the right-hand side, and I'm just left with 0. And if I move the 2 over, I get y is -2. And that's the equation of the tangent line, which is a weird equation for the equation of a tangent line. But I think it'll make sense if I show you the picture. Do you have any questions?
This is the one I needed to see the picture to accept my answer as well.
Daniela, is there anything there I can clarify, or are you good?
Oh no, I think I'm good. Just the difference between this problem and the one that is on the other review is that in this one we have to use the implicit differential, right?
Let me see, where's the other one?
It's number 4.
Yeah, for this one, there was no implicit here because it was solved for y, basically. This is like y equals this.
So we would just take the derivative of that, plug in -1, and then use that for slope.
Yep.
Okay.
Okay, I got it. Thank you.
So for number 5 on this review, would we do the natural log on both sides since it's like something being divided by something else?
For this one,
like quotient rule.
For this one, I think quotient rule is kind of like doable. You know, I mean, you could do logarithmic differentiation. Not sure it's going to save you a whole lot because that fourth power is not on the whole thing. Like if that was x plus 1 to the fourth, you might want to do that. But this is more just a straight up quotient rule, I think, and you'd be fine that way. Whereas if you try and do this one with quotient rule, it'll be a mess. Yeah.
Yeah. Before I realized the log thing, the logarithmic for these, I did the whole chain rule on the one problem on the other review. It took a whole page and a half, and I had to write my answer sideways because I couldn't actually get it to fit on the paper regularly.
Yeah.
So, yeah, it's pretty rough. Oh, and just to be sure, for like the ones where you're saying use limit definition, we can use the f of x plus h minus f of x over h.
Yes. So I had a problem that I ran into a while back. Wasn't recent, but I was trying to make a solar pool heater. Okay, so basically something that my pool pump would run some of the water from the pump through this black irrigation hose, and I'd lay it out in the sun. It would get hot because of the sun, and then it would warm up the water. Okay, so the idea was that I wanted to get this tubing, right, and lay it out in a coil like this and mount it to like a board or something. It was pretty big, 4x8, big old coil. Okay, and when I hooked it up initially, I put the water in here and the hose was too small, so I couldn't get enough flow through it. Okay, I couldn't get enough flow because it had to travel through the entire coil. So what I decided after I built the first version of it is that I would need to instead have 2 lines coming in. And so I needed to cut this coil in half. So imagine if this coil was uncoiled, it would just be this long pipe, right? Like this. And what I needed to do was cut it in half, figure out where the halfway point was without uncoiling it. So can you find me where on this spiral halfway is?
I was actually about to ask that.
Do you understand the question?
Yeah, I'm just trying to think of it like how you would do that. 'Cause I mean, can
It
you
would
do it without
be
knowing the
impossible
full?
to do without calculus. It's impossible to do without calculus. So
Do you have to have the full length straightened out first, or no?
without straightening it, of course, if I had it laid out, I could find halfway, cut it, right? But what I was trying to do, because it was already built, was I was trying to figure out where here do I splice it to be able to feed this into it, and that remaining coil would be half, and the original coil here would be the other half, if that makes sense. So I was able to do it. I haven't looked at this in a long time, and I decided to write some code for it. But here it is. So what is this? Yeah. I did it. I could do it with calculus. If I do, I think it was, how many feet was it?
Will this be like an optimization problem almost? Or you're trying to find the perfect middle or no?
You have to know something about arc lengths. So I knew that this hose was, I think, 556 feet or something is how long it was. And so I needed to know where to cut it so that I'd have about 200, I don't know, 70 or so feet, somewhere around there. So this blue is about halfway. I mean, this is about half the pipe, and then the red makes up the other half. So I knew where to cut it. I knew how many coils to go in and count and then cut. But it is a calculus problem, because if we can find the function that draws this curve, then we can find its arc length, and then we can find out where to stop to have a certain arc length. I'm just showing you this. This is, again, one of those problems where without any mathematical like background knowledge, calculus, then it's just be really hard to do. All right, it's 3:50. Anything else?
I kind of like this change, the flip in position. Now you're the one counting down till 4:30.
Well, we can end anytime. I mean, if no one has questions, we can go.
Professor, do you think the video, like the recording from today, will be available for tomorrow, like on YouTube or no?
Yeah.
Okay.
Is the one from last week up? It should be.
I believe so, because I was
Yeah.
pretty sure I remember scrolling through my YouTube feed and seeing that I got caught on the thumbnail again, so I could see my face doing some
It
random
usually
crap.
takes Zoom about an hour to tell me the video's ready, and then it takes another 30 minutes for me to upload it to YouTube and it be ready for viewing. So from when we stop, a few hours, but I might have to leave, so it may not be till later this evening.
Okay, thank you.
Mhm.
Alrighty, sir. Well, I guess it's that time.
Yeah,
The
I
end
think
of
we
the
should probably
end.
just call it, huh?
Well, I just want to say I did enjoy the semester, sir.
Yeah, me too. I'm looking forward to being on campus, though. I can say that. for sure.
I did my best to try to get into your fall class because I would rather have been there, but unfortunately I could not move around enough things. So the plan now is if I fail in the fall, I'll catch you in the summer or in the spring of 2022.
Yeah.
I mean, I'm hoping it doesn't come to that,
No.
but if I end up switching to like mechanical engineering for a major, would I have to have Cal 3 then? I don't know how that works.
It depends on the degree plan. Depends on where you're transferring to. There's a lot of factors. I mean, now, me personally think, Cal 3 is always a good class to take as an engineering major because you work and do calculus in three-dimensional space. So,
Right.
I mean, you just get more practice with living in that 3D space because everything we do is on a flat sheet of paper here. Pretty much. In Cal 2, we go three-dimensional, but not the way we do in Cal 3. It's different in Cal 3. So, yeah. All right. I may be around later this evening, like I said in my office hours. We'll see. I just found out I might be doing something this evening. So.
Alrighty, sir. Well, I've pretty much got all the reviews done. I just got a few more problems to fix, but we kind of already went over them. So I can make sure I'm good on that. See you Thursday.
Okay. Have a good one, sir.
You too, sir.